Alright, so we're going to talk about transformations. And these are things that are basically going to move our functions around the plane. So if we have just a normal function like y equals x squared, it might move up or down, left or right, or flip itself. And we'll take a look first at an example instead of actually defining this just yet. So if we look at the square root of x, we know what that looks like. And if we wanted to look at the square root of x minus 4, it's just going to shift down 4 units. And most people have seen these before. They just get tripped up a little bit with negative signs if we have a left and right transformation. If we add plus 5 on the end, it's just going to go up 5 units. Now, if we put that on the inside instead, put that back to the origin. So the square root of x minus 3, this is where it's a little counterintuitive. It's going to shift 3 units to the right. Instead, if we add a plus 2 on the inside, that's just going to go 2 units to the left. So when we see that plus on the inside of any function, that's going to tell us to move it left. If it's a minus, it's going to be moving to the right. And the reason it is that way is because it's defined to be a minus on the inside. So technically that's a double minus. Now if we put a negative out front, this is what we call a reflection. That's just going to be a reflection across the x-axis. But if we add a negative on the inside, that's going to be a reflection across the y-axis. So an example, here we have the cube function, so it's centered at the origin, and that's going to tell us to move 3 units to the right and 1 unit up. And that means that our new vertex is going to be 3, 1. In this case, we have the square root of x plus 2, and on the outside we have plus 3 halves. So same thing here, we're going to move 2 units to the left and up 3 halves, and that's going to be our new vertex. So to generalize this, the graph of f of x minus c, notice that's on the inside, is the graph of f shifted right c units if c is positive, left c units if c is negative. And again, that's against our intuition because it's a negative. So if c is negative, it's going to look like it's positive there. The graph of f of x plus d, that d is on the outside in this case, is up d units if d is positive, down d units if d is negative. Now if we put a negative in front of the function, we know that reflects over the x-axis, or if we put the negative inside, it's going to be over the y-axis. Alright, so lastly we want to take a look at what happens if it's not just a negative 1 or a 1 on the outside of the function. So if we have the square root of x again, and in this case we want to consider 2 times the square root of x. So every time we plug in something like 4, we'd normally get 2, the square root of 4 is 2, but in this case we get 2, but then we have to multiply it by 2. And so it's going to go off to infinity a lot faster. Now if we put a 3 outside instead, in this case, when we evaluate the square root of 4, we get 2, but now we're multiplying that by 3, so we end up with 6. Every point's going to just be multiplied by 3 along the y, and so that's going to grow to infinity a lot faster also. So notice that if we keep increasing that value on the outside, it's just going to keep going off to infinity a lot faster. But if we made it something less than 1, it's going to go to infinity a lot slower. So to generalize, the graph of a times f of x is the graph of f of x with a vertical compression if a is less than 1 but greater than 0, and a vertical stretch if a is greater than 1. Alright, so we talked about functions before, and we're used to writing most functions as y equals something in terms of x. In this case, we're going to let y equal f of x, and we're going to rewrite the functions in terms of f of x. And again, this should be a review for most people. We saw this earlier in the chapter also. So instead of writing y equals the square root of x plus 2, it would turn into f of x is equal to the square root of x plus 2. So that x, remember, is our input. And that's going to control what we can plug into the function. And whatever we plug into that is going to go on the right side and replace those x's also. So this is just a really convenient way of being able to evaluate functions. Instead of saying evaluate this thing at 2, I can just say f of 2, or f of 3, or f of t. It doesn't just have to be a number, remember. So f of anything, generalized in this case, is the square root of anything plus 2. Alright, so let's let f of x be 3x squared minus 6x plus 2. And we're going to be asked to find f of x plus h. So notice that those x's, remember, are the ones that are going to be replaced. And that x is our input. So f of x plus h is going to be 3 times x plus h minus 6 times x plus h, that's our input, plus 2. And then we just want to simplify that as much as we can. And that can be the tricky part, because there's a lot of different places that we can make a mistake here. So if we expand x plus h squared and simplify, this is about the best we can do. Now, a definition. The composition f composed g is defined in the following way. So our notation here is f composed g of x, and that's really going to be f of g of x. So really, it's just f with g of x plugged into it. And just want to make a quick note that this is not fog. A lot of people refer to this as fog or FOG. It's not as an O, and it's not a 0 either. It's a really small circle to indicate the composition function. So an example, let f of x be x squared plus 3, and g of x is the square root of x. So we're asked to find the composition of f and g. And by our definition, we just want to write out what f composed g actually is. So this is really going to be f of g of x, which is f of the square root of x. That's really the square root of x squared plus 3, which is x plus 3. And so we're done. Now what about g compose f? Well, same thing. G compose f is really g of f of x, and that means that we're plugging in f to the function g. So this is going to be really g of x squared plus 3. The g of anything is the square root of anything, and so we get the square root of x squared plus 3. Now this last case, we want f compose f. So that's going to be f with f plugged into it. So it's f of x squared plus 3. Now remember that f of anything is anything squared plus 3. So that whole input there is going to be plugged into the function. So we get x squared plus 3, that whole thing squared, plus 3. And this is what we get when we simplify that. Now let f of x be 4x plus 7, and g of x be x minus 7 over 4. In this case, we're asked to find f composed g. And so if we go through this again, f of g of x is really f of x minus 7 over 4. So that's 4 times x minus 7 over 4 plus 7. Now notice that those 4's can cancel, and we're left with x minus 7 plus 7, which is just x. And we could also show that if we did that the reverse, g compose f, we would actually get x as well. And this tells us that f and g have a special relationship. They are inverses of each other. So whenever we have f compose g and g compose f, both giving us x, that tells us right away that f and g are inverses. All right, even and odd functions. So we have a really simple test for determining if functions are even or odd, or neither. If f of negative x is equal to f of x, then f is even. If f of negative x is equal to negative f of x, then f is odd. So determine if the function is even, odd, or neither. And we're given f of x is equal to x to the 4 minus 5x squared. So what we want to do here for our test is write both f and negative f. Then we're going to evaluate f of negative x. And then we're going to compare f of negative x to the things that we wrote in part 1 there. If it's equal to the function, it's even. If it's equal to the negative of the function, then it's odd. So our solution, f of x and negative f of x are both written there. So now for the test. F of negative x is the same thing as negative x to the 4 minus 5 times negative x to the 2. Now remember that we have double negatives there. So those negatives for negative x to the 4 and negative x squared are both going to disappear. So this thing really evaluates to x to the 4 minus 5x squared, which is f. So what does that tell us? It tells us that f is even. And if we looked at the graph here, it is symmetric about the y-axis, and that's because it's an even function. So an example of an odd function, here we have f of x is equal to x cubed plus x. And if we take a look at the graph, we are left with this thing. So to show that this thing is odd, we want to write out f of x and negative f of x. And then we're going to do the test. Remember, we're going to plug in negative x to the function. So we get negative x being cubed plus negative x. Negative x cubed is negative x cubed. And then we have a minus x, which is exactly negative f of x. So that shows that f of x is odd. Now for an odd function, if we look at this graph, we have the point 1, 2, and the point negative 1, negative 2. And that is a property of odd functions. We can generalize that and say that if we have some point AB on an odd function, it's going to correspond to negative A, negative B. So we just showed that even functions are symmetric about the y-axis, and odd functions are symmetric about the origin.